we had, I'd shown you options of SolidCAM 5-axis, and I have the slide in front of me where we did first the multi-blade machining. We also showed turbine blade. I showed you how to machine frame parts using swarfing and 3-axis, and we also did trimming and engine ports. What we are going to do today is we are going to move further into 5-axis and to other areas of 5-axis which is generally not addressed by few systems. So we have 5-axis for doing die mold parts and for styling and also for tire molds, how we machine tire molds. It's not a very specific function for tire molds, but we are going to use some nice functions available to us for tire molds. All right, so let's jump in straight away into the software and open up the die mold part. It's a pretty large part, but we are not going to do everything in this. We are going to do only some specific areas. Which are those areas? I am more interested in machining this area out here. So if I mark those surfaces to you, these are the surfaces that I'm more interested in machining. Now, why did we choose 5-axis to machine these surfaces? For a simple fact that this is in a pretty deep area of the part. So if I have to go in a regular 3-axis, so if I come out of that and go on this way, not the right way, but if you look at the depth that it needs to go, you will need a pretty long tool. And this area is very small. Since this area is very small, you're going to need a very short cutter to actually cut this part, or a small diameter cutter to cut this part. So using a small diameter cutter for such a long length is not a wise thing to do, because you're going to get a lot of chatter or vibrations, because it can't sustain that L/D ratio. So for this, we need to go as short as possible, with as short tool as possible in length, also in diameter. So what I have done now I've done a bit of CAD work here, because I need the tool to be guided by a certain geometry. So I need the construction of the geometry to be done. So what I've done basically is I have created an offset of some surface out here. That's a surface. I've offsetted the bottom surface to create this surface up here, and then marked a point using a 3D sketch. I've marked a point somewhere at the mid of the surface. That's all I need. I just need a point, so I'm going to switch off this surface. And then what I'm going to do is I have done morph between two adjacent surfaces. Which are those surfaces? The first surface is a surface up there. So I'm morphing between that surface and the surface below, which is nothing but a flat planar surface. So I'm going to create the toolpath pattern that is offset from the topmost surface to the bottommost surface. The drive surfaces are all these surfaces that I've picked up. And then I defined the tool. This is basically a short 4-diameter ball nose tool with just only about 25 millimeters out of holder. Even this is too much, but just for the sake of simulation, I have kept it about 25. And what do I have more in the toolpath parameters? I have a maximum step over of 0.4. I can cut it down to 0.2, but to show you a demo, 0.4 should be good enough to show you how it works. Also, I have done a spiral toolpath on this entire geometry. I don't want it to create marks by taking step overs, so I've used the spiral strategy. The only difference now between regular machining of die mold and 5-axis is the tool axis control. And I've used what we call as tilted through point. The point that I created, this point out here, this point that I've created is going to be used to tilt the tool. The tool axis will always pass through that particular point, irrespective of what it is machining, so that it's held and it doesn't change directions on every point. So the axis is always going to pass through that particular point. All right. So we are having the tilt angle. It's taken from the point towards the axis, all right? From the point towards the cutting axis. That's all I need to do, and the gouge check, of course, I have not switched on. If you want, we can switch on the gouge check, only to be checked with the path surfaces, but for this part we really don't need. I'm just going to hit save and calculate. It's pretty quick because since the tool axis is already controlled by me, the software simply has to generate the cuts and pass the passes through that cuts. You can see neat toolpath that's generated. Now if I run this same thing on a machine simulation, you can see how nicely it cuts the part. So let me run it on the machine simulation. Okay, that is the part. And this is my tool. What I'm going to do is I'm going to just switch off these tubes. They sometimes annoy me a lot. Okay, so I have the tool and this is my toolpath. Right. Now let's go step by step because I know that you can't see it continuously on your screen, so I'm going to go step by step. You can see that how nicely and easily the cutting happens. Remember that we are using a very short tool out here, just 20 millimeters out. We can even cut that because we don't see any kind of gouges happening, so you can look. If you're looking at this part from a bit further away, you can see that there is absolutely no gouges happening. And it's doing it in a very fluidic motion. All right. So this can continue till it reaches the bottommost point and it will retract back out. So one of the most critical applications in die mold for 5-axis is to machine these areas where the radius is pretty small. You can't take a small diameter tool to that length because 110% it's going to break, or it will leave a lot of vibrations and chatter on the surface. So one of the most critical applications is to machine such small areas without having to have a lengthier tool of a small diameter, so that you don't get any vibrations. The finish is excellent because you're using the shortest possible length to machine that particular area. All right, let's move ahead. Let's see some other area on the same part. I'm now going to machine, or what we call as a super finishing of some radiuses. If you look at the radius that we're going to cut, I'll just mark those radiuses for you. Show. You can see that the entire radius will be machined using 5-axis, simultaneous 5-axis. Why do we need that? We need because when you're doing in 3-axis, even in your rest machining in HSM, sometimes it is not possible for you to use really short length tools. What does it do basically is it creates chatter on the surfaces where the tool tries to approach, in where the L/D ratio goes up. In such places you will see chatter and vibration coming up, especially when you go into this region out here. It's really very difficult to cut this part without chatter or vibration. So what I've done is I'm going to use now full 5-axis with full gouge control to cut only these fillets. So what do I have in my process? I have the strategy that is morphed between two curves. If you look at the upper curve, that's the upper curve, and then you have the bottommost curve. So if I show that the end edge or the bottom curve, that's the end edge curve, and these surfaces that I just showed you, which are the drive surfaces. However, we have a problem here. The problem is that these fillets are changing their vector directions very quickly. If you look at the vector direction at this point and if you look at the vector direction at this point, it's completely different. So if I use a regular guiding strategy for the tool axis control, if I use a regular one, I'm going to be in a major in major problems, because the tool will tilt drastically from point A to point B, and that could cause, one, tool breakage, two, it could also cause machines to get damaged, because you could have a part hitting up on your machine spindle and stuff like that. Now, to avoid that, what I've done is I have created a 3D sketch. It's nothing. How have I done it? I simply have created another set of offset surface up here, and then extracted the center curve of this particular, of all these surfaces. And not just only extracted a center curve, because the center curve, for example, in this case would create a lot of sharp corners when they're joining. So what I've done is I've converted that particular sketch into a spline. Spline with a very large tolerance. If you look at the tolerance, it could be anywhere between 5 to 10 mm. So what this tolerance basically does is it removes the sharp corner and makes that area smooth by putting a fillet in between those two edges. And thereby it gives me a very nice curve to follow the tool, or to make the tool guide on those areas much smoothly. Let me switch off, and I have my tilting curve. So if I edit the toolpath again, and if I go to the tool axis control, I've got tilted through curve, and this is my curve out here. I'm going to tilt the tool, or the tool axis is always going to pass through that particular curve, irrespective of which area it is cutting. The axis will always go through the curve. And what is the sub strategy in the tilt that I've used? I've used the closest point. That means the closest point on the surface will be mapped to the closest point on the curve, and the axis will pass through that. Right. In the gouge check, again, I have not defined anything, because generally if you're cutting without gouge check, it gives a pretty good result. It doesn't mean that you can't give gouge check. Of course you can. You can give all kinds of gouge checks, but we don't need, in this case, the gouge check. I'm just going to hit save and calculate. Okay, that's done. Let's run the simulation, and let's look first at the toolpath, how it looks in the host CAD. It's a nice smooth toolpath. It's starting from this region out here and goes all the way up into this area. I call this a garland area because it's looking like a garland. So it goes into this area smoothly, comes up, and it goes further. Now it will not look very nice in this, but it will look very nice during the machine simulation. So let's go into the machine simulation. Right, so we have the toolpath out here, and the part mounted on the machine. Again, as usual, I'm going to switch off the tubes. I can completely switch them off in the machine, but my customer needs them, so I've kept it. So let's go line by line and see how it behaves. I'm more interested to know how it behaves into this deep area. Very nicely, it's continuously following that area. And as it goes into this garland, you can see that it's very nicely going inside. Absolutely no gouges on any side. It's clearing that part very well because the tilt curve is taking care of all that problems. Let's move slowly. It's clearing it. Now it's come to the deepest point. I can see how close the holder is to the part. But still there are no gouges because it's pretty safe. Let's clear that area. Now it's going to come up. Okay. And it's out of that area. It's now going to machine the remaining part of the fillet. Now imagine the kind of finish that this particular process would give you, because you're using the shortest possible tool. You can see it's hardly out of the holder by about 20 mm. And it's cutting the entire area beautifully. You're not going to have any scallops remaining on this part. You won't have any vibration marks because you're using a very short tool, so it's very rigid. And it's generated directly on the NURBS surface. Very nice. So using the regular 5-axis strategies, you can actually create toolpaths for any part of this area. And what does it, the greatest benefit here is it allows you to use the shortest possible tool to cut the entire part, to cut portion of the part, or you can use it to cut the entire part, again by defining several zones of cutting. So these are the two nice examples that I could give you up in explaining simultaneous 5-axis for cutting die mold parts, especially for finishing areas where you feel that big, small diameter tools with longer length could cause problems. Right. Let's move into another area. Now we have done the fine features. We have also done the superfinishing. Let's move into the 3 and 5-axis conversion. Since we are still in the die mold segment, let's check this area also. So I'm going to open another part. Okay, I'm going to unsuppress Toolpath, and I'm going to delete. Let me check this. Okay. Right. So I'm going to delete this, and I'll show you what this toolpath looks like. Now this is a regular HSM toolpath. Okay, it's a regular HSM toolpath, and you can see that if I look at the height, the part height is about 66 millimeters. So if I have to really go down to machine this entire part, I would need at least, if not 66 millimeters, I would need at least this height of about 41 millimeter. A 41 millimeter tool, let's say about 6 diameter, would be about an L by D ratio of more than 6. This again can cause vibrations. This again can cause chatter. So now I would like to convert this 3-axis toolpath into 5-axis. By doing that, I can use shorter tools and approach these deep areas like what we saw there. But here, I don't want to use all those methods of putting a tilt line and creating a 5-axis toolpath. What I'm going to do here is, I have a created 3-axis toolpath. I would like to convert this 3-axis toolpath to a 5-axis toolpath. How do I do it? Simple. Right-click on the operations. I'm going to add convert HSM to simultaneous 5-axis. And my source operation is this particular HSM operation. My cut tolerance, I'm not going to change. It is 10 microns before, it is 10 microns now. The conversion link type, I'm going to use a source link. And the tool, I'm actually going to use a shorter one. You can see that we had a longer tool, and now I'm going to use a shorter tool. Just 45 millimeter out of holder. Select. Go to levels. No change because I'm going to use the default of HSM. I'm not going to change that. In the tool axis control, I'm going to be tilted by a fixed angle to my Z-axis. Okay, and that angle is 0. So I'm allowing the software to not tilt beyond this angle that I've defined. And I'm allowing the tool axis to cross the tilt axis. So I'm going to go beyond what we call as our pole angle. And in the gout check, however, I'm going to enable gout check. And this is against the check surfaces. Which are the check surfaces? The check surfaces are basically these surfaces. These are my check surfaces. And I would like to check holder and the tool tip. Anything else in between this is not really needed. And we would like to go with the tilted to tilting tool away with max angle, and use a subtilt type as 3-axis to 5-axis conversion. Stock to leave, 0, we are not going to touch that. Okay, and in the sub-advanced options that we have, I'm going to use a default wherein if the tool does not fit a certain area, I'm still going to keep the 5-axis, but I'm going to keep it close to 3-axis solution as much as possible. Where the tool does not fit in a very short distance, I'm going to go back to 3-axis because I don't really need 5-axis there. And where the tool does not fit in a longer distance, I'm going to go back again to 3-axis. And this is the standard advanced options that I'm going to use. And I'll just hit save and calculate. It'll be some few minutes before it's completed its calculation. Sorry, HSM uses a tessellation, and the 5-axis conversion directly works on the surfaces or the NURBS surfaces. So since there are two kinds of engine involved, the gouge check of the 5-axis engine works on the surface, and it's much more accurate. So even if there is a small amount of dig, even we're talking about 4 to 5 microns into the part, it will be shown as dig inside the 5-axis engine. And then it turns into the new functions that we have in levels called levels in clearance called as the remaining collisions. So if there are collisions still remaining after it has done the conversion, what it basically does is it comes to this area and finds out what it needs to do with those collisions. By default, I've set the values or the options to trim colliding contours and relink. That means any contours that are colliding or that have collisions will be cut, and they'll be retracted to a safe position and relinked to the next area out here. So it's precisely doing the same thing. Now this remaining collisions could be on the cut part or it could be even on the links. So it checks both of them. Now to avoid these kind of retractions in conversion, you simply keep the collisions because HSM has already done the collision check for you with a tolerance of about 10 microns and it has not found any issues with it. So you would like to keep the same tolerance or the same results coming out from HSM inside your conversion. So let's recalculate this part again. Yes. Take about a minute or two to calculate. Okay, that's done. So what you'll see now here is those retracts have disappeared because I have not used the trim colliding contours and railing both for my links as well as my cutting passes. So now if I look at the simulation, we did not go into the machine simulation, but I would like to have both the holder and the tool, and let's run it down very quickly. So you can see as it touches down, as it goes below and the holder comes in contact with the part area, it's now starting to tilt itself. So you can actually start using short tools and go deep into this part. Let me go down further. And let's run slowly. Now what's the nice thing about this is it's trying to maintain the tilt as close as possible. For example, when it is inside, it tries to go as close as possible to the tilt, but when it comes out, it knows that it's no longer going to tilt, or it no longer needs to be tilted, so it starts becoming as close to the 3-axis solution as possible, which is what I wanted it to do. Again, when it's going inside, since the holder is going to come very close to the cut point or to the cut area, it tilts the tool. So with this, I can actually use a 3-axis tool path, convert it easily and smoothly to 5-axis. And thereby I can use shorter tools, get much better surface finish, much better cutting parameters. Let's see what happens out here. It's again trying to be straight because there's another fellow coming up here. It can't tilt too much. And again, as it finishes, it's going to go into tilting again. So you can see that it was pretty easy. Just take the tool path, set your conversion to 3 to 5-axis conversion, calculate. You can use short tools, cut deeper into the part without compromising on parameters or surface quality, or for that matter even gouges. Your toolpath is checked for gouges 100%. All right, let's finish this and let's open another part, not the STL. Since we are in the die mold, I would like to open up the drilling. So I have got a part now, and I would like to do the drilling of all these holes in one go. Now all these holes have different orientations because they are normal to some surface out here. So each of them have different orientations, they have different directions, and they have different depths. If I'm not wrong, they have different depths. So I would like to do this in one shot. For this exact operation, we have got a solution in SolidCAM, and that's the 5-axis drilling. So let me add 5-axis drilling or multi-axis drilling in this. And all I need to do in the geometry is to select new. And click on Find Holes. The moment I hit that, I get, first of all, the groups in terms of shapes. So I've got shape 1 and I've got shape 2. You can see that there are some holes that it also recognizes from the bottom. Now, since this particular face is going to be mounted or directly on the machine bed, or it's going to be held in the vise, these 4 holes are practically impossible to do. So these 4 holes need to be excluded from our cutting. So what I'm going to do is I'm going to right click on shape 2 and I'm going to say remove. So I've removed the shape, that's those 4 holes, and all I have is those 6 holes on top in different directions. Right. Let's click OK. Let's select the tool. I'm going to use a 6mm drill to cut. If you look at the levels, my depth is already set. So if I go into the depth edit, I can get the depth of each of these holes. I can have the depth of each of these holes. I can edit the depth of each of these holes. For example, this particular hole, I would like it not to go to 15.079 and 097, but I would like it to stop at 10mm itself. So I have edited the depth of this particular hole. The moment I do that, it puts it into a second group because the depth is different. It colors it and says that this has been manually edited. The depth has been changed to 10mm. Okay, I'll agree. Go to the technology, and I'm going to use a pecking cycle. And in the pecking cycle, I will say my step down is 3 mm. Full retract, no. I wanted to just retract to the safety distance of 2 mm above every position. Okay, that is done. And the tool axis output format, I get either 4-axis or 5-axis. I want a 5-axis output. Save and calculate. Now if I look at the toolpath, this is how my toolpath looks like. We can take this now to machine simulation. And go hole by hole, how it looks like. Let's go position 1. This is 1. You can see that the software is showing this as a gouge. It's obviously a gouge because the hole diameter is 6 and the tool diameter is 6. So it's precisely 6 and 6 matching. So it is showing me as a collision, but that's actually not a collision. It's just a rubbing of the tool with the hole geometry. Okay, this is done. Retract up, goes to the next one. That's the next hole, down, and then it goes again, retracts to the next hole, yes, again it's finished. It's now going to retract to the next hole out here, and it's machining, retract, next hole. I didn't specify the angles. The angles has been found directly by the software using the vector directions of the holes. Again, that's it. So you can see how easy it was to generate the program for drilling in different directions using 5-axis. Just select the part, click on Find Holes, generates different shapes of holes. You can choose which shape to cut, which shapes not to cut. For example, we excluded 4 holes from the bottom that were practically impossible to machine, so that was completely excluded, and we generated straight away the tool path. If I output this, If I generate a G code, okay, we have switched on the header, so let me modify. I'm going to change some things in the post processor. Save this, and let's take another output. Okay, so you can see that we're calling the cycle 203. This is basically for Hyder 9, and we have already indexed, or we have already moved the B and C axis to that position, and then we are calling up the cycle. Retract, going to the next position, and the cycle is called again. All right, so we touched upon the die mold, we touched upon conversion, we also touched upon the 5-axis drilling, and what now remains basically is the STL. So I'm going to show you immediately the STL. So let's open, and let me open the files. SolidCAM, the webinars, STL. Okay. Let me open this. Right. So we have a very nice statue that we'd like to machine. Now the problem with STL is they're basically made up of triangles. Millions of triangles, and it's virtually impossible to cut each of these triangles by selecting them as a geometry. So what we have in SolidCAM is we have got a combination of STL direct machining for 3-axis, and then using STL as a guiding geometry, we machine some surfaces and project back the toolpath on the STL geometry. So what we have here is, we will I'll just delete this toolpath, we don't need it. I'm going to calculate the first toolpath, which is nothing but a 3-axis toolpath. That's very fast. So if you look at the 3-axis toolpath now, if I show you the simulation in Solid Verify, that's the block that I have. And let me cut very quickly. No holder needed. Remember that the part geometry that I selected was only the STL geometry. So from the first setting, this is what is achieved. Right, let's calculate the other two toolpaths, which are nothing but rest roughing toolpaths for HSM. And then we will jump into the 5-axis calculations for this particular part. And I'll show you the underlying principle on how we do the calculations for 5-axis. Which also brings me to a very interesting topic, and that is about the multi-core support. I'd like to show you how it utilizes the cores. You can see that my entire CPU cores are loaded, and once it is done and once it starts calculating again, you'll see that my cores get loaded 100%. You can see the distribution of the load on the cores. It's using the entire set of 8 cores that are available to it for calculation. All right, that's done. So if I now run the simulation of these two areas, Solid Verify 3D. Okay, let's run play. No. That's from one side, and then I have the second side, or the third setting that I have done is to machine the other side of this part. Right. So we have done the roughing. Now I would like to use 5-axis principles for finishing. What I've done is I've simply taken up a couple of areas. For example, I've got one area up here that is from this portion right up to the chin of the model, and then the entire part itself on how we do the machining. So what do we do in STL machining? How we do it? What we have basically is we have some surfaces. So if I switch off the main STL geometry, I've got some guiding surfaces with me which are inside the STL. This was generated later on after we got the STL data inside SolidCAM. I generated these guiding surfaces. Now I'm going to use these guiding surfaces to actually calculate the toolpath. For example, if we look at this area out here, I'm using morph between two curves. So the geometry, this is the surface that I'm going to cut. And then I have the starting edge curve and the ending edge curve. So I have two curves and that geometry. I'm using a 12mm ball nose. In fact, I can use a shorter one, so I'm going to copy this and reduce. Because we are using 5-axis, I'm going to reduce this length. So I have a short tool here, and in the tool axis control, I'm going to use a 25-degree tilt so that it's tilted so that I can use even more shorter tools. And in the gout check, however, I'm going to use retract along tool axis, and I've selected the STL file as my gout check geometry. So let's quickly check and calculate how it looks like now. Right, the calculation is already done. That's very fast. I don't want to see this one, but I would like to go to the host CAD to see how my toolpath looks like. So if I go step by step, you can see that it's much above the surface that was used to calculate, because it's already projected the toolpath onto the STL geometry that we selected for our calculation. You can see that this geometry was nicely projected on the STL geometry. So what we did was we basically selected the bottommost surface, we created the toolpath, and just then projected this toolpath along the tool direction on the STL geometry. Very easy, very simple. And you can use shorter tools to cut any kind of STL geometries without having to convert them to any kind of surfaces. So if you really want to cut, let's say, scanned parts done by white light scanning or done by even probing, you could directly take the STL geometry from the scanner and start cutting in 5-axis straight away. Let's see another area that we did in 5-axis, and that was to use the complete geometry. For example, I created a very nice, a simple elliptical shaped surface inside the STL geometry, and then use the morph between two curves to cut this geometry using, that's my first curve and that's my second curve. So I have morphed the geometry between these two curves and then used, let's use the same tool. Okay. Tool axis control, it's 0 because I'm now going to go normal to that surface. And in the gout check, again, I've selected the STL geometry as my gout check geometry. So I don't need much. Just simply hit save and calculate. So there are 304 cuts that it has derived, and these 304 cuts, after they're calculated on the surface, will then be gout checked and projected back onto the STL geometry. Okay, the calculation is done. Let's run the simulation. I'm going to switch off the tool so that it's very quick. All right, we do have problems, couple of problems. The problem is here. You can see that it's not projected a certain area onto the STL geometry. And why would that be? That's because the tool length that we defined was much smaller than the difference between the surface and the STL. So that is the reason it could not project that. So what we're going to do is we're going to select the old tool again, and I'm going to recalculate this whole thing again. And you'll see that how nicely and easily it projects back the toolpath. Right, this also is done. Let's look at the toolpath. As you can see, we don't have any more areas that have not been done. And you can see how nicely the toolpath was lifted up and projected onto the STL geometry. And this is machined following the principles of 5-axis. So it's actually going to rotate the entire table to keep continuously machining this particular STL face geometry that you have seen on 5-axis. So using these principles of projection available in SolidCAM 5-axis simultaneous, you can cut any kind of STL geometry. It doesn't matter from where the sources come. As long as you have the STL geometry, you can create those guiding surfaces and cut the part straight away. Right. As we come towards the end, I would like to show you another application of SolidCAM 5-axis. Not the STL, sorry, but it's basically the tire. Okay, here I have the tire segment. How SolidCAM is used to cut such segments. Now, the initial roughing has been done using iMachining 3D, so I'm not going to be touching on those areas. I've also finished, for example, if I keep showing you the simulation, I've also finished these two surfaces using HSS, so that's surface 1. If I go to the next toolpath, that's how it's been done. And then what I have done basically is I have blocked, or what we have done basically here is I have blocked all these projections using a nice smooth surface, and that surface is out here. So if I, not that one, yes, this one, and this one, and this one, of course. So if I show you the surface, it's been blocked using these surfaces. So what I did was I roughed out the entire thing up to this surface without the projections. So what I get simply is some nice smooth surface from where I can start carving out these profiles using 5-axis. So once I have finished the machining of those surfaces, I can carve out. How did I carve out these toolpaths? I've shown in this case both the examples. One, if I use a regular HSM rest rough, this is how my toolpath will look like. But then I'll have to use a pretty long tool because I need to go to the deepest point from the topmost point. So this kind of principles are generally not used in tire mold. So what I've done, I've used something called as parallel to surface machining. So if I show you the parameters, parallel to surface, and these are the surfaces that I need to cut. the ones that are marked in blue. Those are the surface I need to cut. And the strategy is to go parallel to the bottommost surface. Okay, so how does a toolpath look like? If I run the simulation, you can see very nice, straightforward toolpath using parallel to surface, only machining the area that I wanted to cut with nice ramping and using full 5-axis principle, so I can use really short tool in this. So if I run now maybe the machine simulation, you can see how it looks like. Okay, that's a DMU 60T. So if I run block by block, you can see how nicely it's turning around. What it is doing now is it is ramping the internal areas, and after ramping is done, it moves to the next one. It keeps evacuating the center position till it reaches to a point where it can cut continuously. Okay, still don't have any issues. Okay, back again. So what we did now is to evacuate the center material of those ribs using 5-axis and a taper milling tool. Why taper milling is because we need to go into the furthermost corners as much as possible, so that's the reason I've used a taper milling, a taper flattened mill. Okay. After that is done, what I've done here is, if I run the simulation, not the machine simulation of course, I'm going to go into the host CAD. I have shown how we can remove material in this region out here. And we have used parallel to curve, and I've used the morph pocket functionality to remove the material in between those curves. So it's basically, if you look at the geometry, so if I show you the geometry, that is the geometry that was used, and I've gone parallel to that, machining the two surfaces in between to evacuate the material out in between each of these areas. Right. What next? Then we have used morph between two surfaces, or curves rather, to evacuate or to finish the entire thing. In fact, this is a pretty lengthy toolpath, and I've used the same principle that you saw in STL machining. I machined a dummy surface and then projected the entire toolpath on the entire projections. This is one way of finishing the mold. We have projected the entire toolpath from the bottommost surface up to the projections. So we create a simple clean toolpath, and like we did in STL, we project it back. But sometimes this is not the best way to do it. That's the reason I've shown you different ways on which you can cut this part. For example, how to cut this area out here. We've used parallel to curve and done the bottom edge machining. Now if we go again to the next area, I've done a very interesting machining out here. This is to generate the bottom sharp corners that will be left out after using a ball nose tool. Now if I run the machine simulation, it's going to be very evident on why I think this toolpath is interesting. Okay. If you see, there are a lot of retracts. Now I'll tell you why these retracts are coming as we move into the toolpath. I'm going to switch off the toolpath. Okay, we're going to zoom into that area. So what it is doing, it is rolling on the external corner. That's fine. Okay. And as it goes into the internal corner, as it goes to the internal corner out there, it's very difficult for it to change the angle or to change the tilt in a very small and a restricted area. So what it basically does, it retracts back. Very smart operation by SolidCAM. It changes the tilt to the next possible angle and then approaches back the corner and continues machining. So wherever there is an internal corner where it can't change the tilt, quickly in that very small area, in the very niche area. It retracts out, changes the tilt in air, and reapproaches the area back. It's a very interesting thing. So if I show you the tool path, you can see at every internal corner it has retracted the tool out, changed the tilt, and come back again into the area. So it's pretty interesting on how this tool path has been done, and using this mechanism all other tool paths have been done in a similar fashion. So if I look at the next one, this has been done specifically to cut the sharp corner out here. We have done single line parallel to curve tool path, and that will be helpful for cutting the sharp corners out here. And then you have parallel to surface. This is for generating the sharp corners for this projections, like exactly the way we did earlier for the earlier part. And to end it, I've done a parallel to surface again to machine the same corners. And you can look what happens here. When it goes into the internal corner, it's retracting the tool out, changing the tilt, and coming back again to that area to continue machining. So using the functionalities provided in SolidCAM 5-axis, you can actually end up machining any part in any kind of strategy that you would like. Whether it is, so if I can go back and summarize, whether it is a aerospace part, that's either a multi-blade, turbine blade, or a frame, or it could be an automotive part. You could trim a vacuum form part, you could cut an engine port, you could cut tire molds, or it could be a die mold. You could machine fine features, you could convert 3-axis tool parts to 5-axis. You could do superfinishing using shortest possible tools with 100% gouge check, multi-axis drilling, and then you could do some STL machining of parts that generally don't need any surface creation. Directly you could machine on those millions of triangles in 5-axis. So you can name the part, you can name the application, and SolidCAM has a solution for you in this area. All right, with this we come to the end of those series of 2 webinars. If there are questions, I'll be more than glad to answer your questions.
Thank you, Ahmad. I see that we don't have any questions today, so I want to thank you again, and thank you everyone for joining us today. And we will see you next week, same time, same day. Hope you have a nice week and nice weekend. See you. Bye.